Welcome back. It is good to have you here as we begin this foundational journey into occupational safety and health. This content is for informational and entertainment purposes only and does not constitute formal legal compliance or professional safety advice. This is an unofficial, independently produced course and is not affiliated with, endorsed by, or connected to the Occupational Safety and Health Administration, OSHA, or any official certification body. Always consult a qualified professional or official regulatory guidelines before making legal, compliance, or safety decisions. This initial chapter introduces the core framework that governs workplace safety across the United States, providing the essential context you need before we dive into specific technical hazards. Over the coming modules, we will examine the history, mission, and legal architecture established by the Occupational Safety and Health Act of 1970. You will learn how the regulatory agency enforces compliance, how inspections are conducted, and how injury record-keeping functions to prevent workplace fatalities. Understanding these systemic mechanisms is just as critical as knowing how to mitigate physical hazards, as it establishes the legal and cultural baseline for every safety protocol you will encounter. By mastering these fundamentals, you will not only prepare yourself for compliance, but also understand the underlying philosophy that drives modern industrial safety standards. Investing your time in this comprehensive course is a deliberate decision to build a highly valuable professional skill set that directly protects lives and ensures organizational sustainability. Throughout this training, you will gain actionable insights into walking and working surfaces, emergency planning, electrical hazard prevention, personal protective equipment, and hazard communication standards. This knowledge is not merely academic. It translates into the practical ability to identify noncompliance, implement effective safety programs, and foster a robust safety culture within any general industry sector. Equipping yourself with these competencies makes you a vital asset to any operational team, significantly reducing liability and keeping workers safe. Let's get started with our first deep dive. See you in the next lecture. Welcome back. When we consider safety in a general industry context, our focus often naturally gravitates toward spectacular hazards like high-voltage electrical installations or heavy machinery components. Yet, a rigorous analysis of workplace injury metrics invariably points to a much more pervasive source of risk that exists literally beneath our feet. Walking and working surfaces represent the foundational infrastructure of any industrial facility, and their mismanagement represents one of the most consistent contributors to occupational injuries and fatalities. To address this risk systematically, the Occupational Safety and Health Administration provides a comprehensive regulatory framework under 29 CFR 1910 Subpart D. This subpart establishes performance-based and prescriptive criteria designed to eliminate the environmental conditions that cause slips, trips, and falls. Our objective in this discussion is to deconstruct these requirements, examining how proper surface maintenance, structural inspections, and engineered protection systems function together as a coherent safety architecture. The baseline requirement for surface safety begins with housekeeping as codified in Section 1910.22, which dictates that all places of employment, passageways, storerooms, and service rooms must be kept in a clean, orderly, and sanitary condition. In practice, this means that floor surfaces must be diligently maintained free of accumulated debris, loose materials, or sharp and protruding objects that could compromise stable footing. Furthermore, the standard explicitly demands that the floor of each workroom be maintained in a clean and, to the extent feasible, dry condition. Where wet processes are an inherent part of the operational logic, adequate drainage must be engineered into the floor design, and the employer must provide dry standing places such as false floors, platforms, or high traction mats. It is a common misconception that housekeeping is merely an aesthetic concern, but from a safety engineering perspective, an uncontrolled spill, or an irregular floor surface represents a latent defect in the workspace infrastructure that will eventually manifest as a systemic failure when an employee interacts with it. Beyond cleanliness, a fundamental structural constraint imposed by Subpart D is that every walking and working surface must possess the capacity to safely support its maximum intended load. This capacity must account for the cumulative weight of employees, tools, portable machinery, vehicles, and stored raw materials or finished products. To manage this risk, any elevated surface or floor area utilized for storage must have its approved structural load limits clearly marked on highly visible, durable plates affixed by the building owner or an authorized agent. This structural integrity extends to the vertical and inclined elements used for transit throughout a facility, specifically stairways and ladders. For example, fixed industrial stairways must be engineered to carry a minimum concentrated moving load of 1,000 pounds or 5 times the anticipated live load, whichever is greater. When workers introduce dynamic loads by moving heavy equipment up or down stairs, or when they overload an elevated platform beyond its calculated threshold, they risk a catastrophic structural collapse that bypasses localized fall protection systems entirely. Stairways and ladders serve as critical access points, but they also introduce concentrated elevation hazards that require specific geometry and maintenance to remain safe. Under the current federal regulations, any flight of stairs containing 4 or more risers must be equipped with standard handrails or stair rail systems to provide continuous physical support. These handrails must be installed within a precise geometric window, specifically between 30 and 38 inches measured from the leading edge of the stair tread to the upper surface of the rail. Turning our attention to ladders, the rules differentiate strictly between portable and fixed variants, yet both require meticulous pre-use inspection protocols. Portable ladders must be inspected by a competent person for structural defects, such as cracked side rails, broken rungs, or failing hardware prior to every single shift. When deploying a portable extension ladder, it must be positioned at a stable angle where the horizontal distance from the top support to the foot of the ladder is approximately 1/4 of the working length of the ladder itself. Additionally, the side rails must extend at least 3 feet above the upper landing surface to guarantee a safe transition zone for the worker. Fixed ladders and specialized scaffolding elevate the level of risk and consequently require more stringent engineering controls and weight capacity factors. Fixed ladders that extend beyond 24 feet above a lower level must be equipped with an active ladder safety system or a personal fall arrest system, a rule that effectively phases out the historical reliance on traditional cages and wells, which failed to reliably arrest a falling body. Mobile ladder stands and scaffolds must be capable of supporting at least 4 times their maximum intended load without structural yielding. When dealing with scaffolds, general industry employers must align their practices with the rigorous criteria found in the construction standards, which mandate regular inspections by a competent person before every work shift and after any event that could compromise structural stability. Wheels or casters on mobile units must be equipped with positive locking systems to completely prevent horizontal movement while an employee is elevated on the structure, neutralizing the tipping hazards associated with shifts in the center of gravity. Industrial facilities frequently feature specialized zones where the floor plane is intentionally interrupted, such as loading docks, maintenance pits, and mechanical floor openings. These configurations present severe edge hazards where a single misstep can result in a fall to a lower level with significant kinetic impact. Loading docks are high-traffic interfaces where mechanical handling equipment and pedestrians intersect, demanding clear aisle markings and robust dock boards that are securely anchored to prevent slipping during material transfer. Floor holes, defined as any opening measuring 2 inches or more in its least dimension, must be protected by a cover of standard strength or guarded by a permanent rail system on all exposed sides. Similarly, Infrequently used maintenance pits or hatchways must either be protected by flush fitting covers capable of supporting anticipated traffic loads or constantly attended by a designated spotter whenever the cover is removed. Neglecting to guard these openings, even for brief operational intervals, creates a severe non-compliance trap that accounts for a substantial percentage of catastrophic workplace accidents. To mitigate these persistent elevation risks, Subpart D dictates the mandatory implementation of fall protection systems whenever an employee is exposed to a fall hazard of 4 feet or more to a lower level. The primary, non-invasive method of protection is the guardrail system, which must feature a top rail height of 42 inches, plus or minus 3 inches above the walking working surface. This system must also incorporate an intermediate rail positioned halfway between the top rail and the floor, along with a continuous toe board at least 3.5 inches high to prevent tools or materials from falling over the edge. When engineered barriers like guardrails are structurally unfeasible, employers must transition to personal fall arrest systems, which consist of a full-body harness, an anchorage point, and a connecting element like a deceleration lanyard. The selection and maintenance of this equipment cannot be treated casually. All personal fall protection components must be inspected for wear, fraying, chemical damage, or mechanical failure before each use, and any component subjected to an actual fall impact must be immediately removed from service permanently. See you in the next lecture. OSHA Plus 7. Welcome back. Today we are going to examine the structural and procedural requirements that ensure personnel can safely evacuate a workplace during crisis. Every workplace must possess a continuous and unobstructed path of exit travel from any point within a workplace to a place of safety, which OSHA formally defines as an exit route. An exit route is structurally comprised of 3 distinct, mandatory components: the exit access, the exit itself, and the exit discharge. The exit access is the portion of the route that leads directly to an exit, such as a hallway or aisleway, and it must remain completely free of storage, equipment, or locked doors at all times. The exit itself is a separated path that provides a protected way of travel, typically separated from other workplace spaces by fire-resistant materials, such as a rated stairwell. Finally, the exit discharge leads directly outside or to a street, walkway, or open space with access to the outside. Each of these 3 sections must be designed to support the maximum intended occupant load of the building, meaning that the ceiling must be at least 7 feet 6 inches high, and the width must be at least 28 inches wide at all points. Management must ensure that exit routes are unobstructed, meaning that no materials, decorations, or machinery can block or obscure the view of an exit door. Furthermore, any door along an exit route must remain unlocked from the inside, swinging outward in the direction of travel if the room is designed to occupy more than 50 people. Proper visibility and marking of these routes are just as critical as their physical dimensions to prevent confusion during a sudden power failure or smoke accumulation. OSHA standards dictate that each exit must be clearly visible and marked by a sign reading "Exit" in plainly legible letters that are not less than 6 inches high, with the principal strokes of the letters being not less than 3/4 of an inch wide. If the direction of travel to the nearest exit is not immediately apparent to occupants, signs must be posted along the exit access indicating the direction of travel with clearly visible directional arrows. Any door, passage, or stairway that is neither an exit nor an exit access, but could be easily mistaken for one, must be clearly identified with a sign reading "Not an exit" or labeled for its actual use, such as storeroom or closet. To ensure visibility during an emergency, these signs must be continuously illuminated by a reliable light source, giving a value of at least 5-foot candles. If a workplace relies on artificial lighting, emergency illumination must be provided to keep the exit routes lit if the main power grid fails. Routine inspections are necessary to ensure that burned-out bulbs are immediately replaced and that backup battery systems are fully operational. When a crisis occurs, structural exit routes are only effective if the organization executes a well-coordinated response governed by an Emergency Action Plan, or EAP. This plan must be written, kept in the workplace, and made available to employees for review, though employers with 10 or fewer employees may communicate the plan orally. At a minimum, an EAP must detail the explicit procedures for reporting a fire or other emergency, the designated evacuation types, and the exact route assignments. It must also include procedures for employees who remain behind to operate critical plant operations before they evacuate, as well as accounting procedures for all personnel after evacuation is completed. To ensure the plan works, employers must designate and train specific employees to assist in the safe and orderly evacuation of other staff. Alarms must be distinctive and recognizable to all employees, serving as a clear signal to initiate the evacuation actions specified in the plan. Training must occur when the plan is initially developed, whenever an employee's responsibilities under the plan change, and whenever the plan itself is revised. Alongside the evacuation protocol, a workplace must implement a written fire prevention plan to proactively reduce the likelihood of a fire occurring in the first place. This plan must list all major fire hazards, proper handling and storage procedures for hazardous materials, and the potential ignition sources, such as welding or smoking. It must explicitly identify the type of fire protection equipment necessary to control each hazard, assigning organizational responsibility for the maintenance of those systems. The plan must also document the names or job titles of the employees responsible for maintaining equipment to prevent or control sources of ignition or fires. Accumulations of flammable and combustible waste materials must be strictly controlled, requiring regular disposal to minimize fuel loads. Heat-producing equipment, such as boilers or commercial machinery, must be kept clean and properly maintained according to strict schedules to prevent accidental ignition. Employees must be informed of the fire hazards to which they are exposed when they are first assigned to a job. Fire protection equipment, particularly portable fire extinguishers, serves as an immediate line of defense to control small fires before they escalate. Employers who choose to provide extinguishers must select and distribute them based on the specific classes of anticipated fires within the facility. Class A extinguishers are meant for ordinary combustibles like wood and paper, Class B for flammable liquids, Class C for electrical fires, Class D for combustible metals, and Class K for commercial cooking media. Extinguishers must be mounted, located, and identified so that they are readily accessible to employees without subjecting them to potential injury. The travel distance to Class A or Class C extinguishers must not exceed 75 feet, while the travel distance for Class B extinguishers is limited to 50 feet due to the rapid spread of liquid fires. Employers are responsible for the inspection, maintenance, and testing of all portable fire extinguishers within the workplace. This requires a visual monthly inspection to verify that the pressure gauge is in the operable zone, the nozzle is clear, and the tamper seal is intact. Furthermore, an annual maintenance check is required, and the date must be recorded on a tag attached to the extinguisher to prove compliance. That concludes our analysis of emergency paths and planning frameworks. See you in the next lecture. Welcome back. When we look at industrial safety, electricity presents a unique challenge because it is an invisible hazard. Under 29 CFR 1910 Subpart S, OSHA lays out strict design standards and work practices to protect workers from the inherent dangers of electrical systems. The primary physical risks we face are electrical shocks, arc flashes, and thermal burns. A shock occurs when a human body completes an electrical circuit, becoming the path of least resistance to the ground. This can range from a mild sensation to ventricular fibrillation or complete cardiac arrest, depending on the current level and path. An arc flash, on the other hand, is a violent release of energy caused by an electrical fault that ionizes the air, creating temperatures that can exceed 35,000 degrees Fahrenheit. This extreme heat causes severe arc burns and can ignite nearby clothing, while the accompanying blast pressure can cause secondary mechanical injuries. ECFR. To systematically mitigate these threats, industrial infrastructure relies on specific engineering controls, namely insulation, grounding, and overcurrent protection. Insulation uses non-conductive materials like plastic or rubber to completely enclose live conductors, preventing accidental human contact. Grounding creates a secondary, low-resistance path for electricity to flow safely into the earth if a fault occurs, ensuring that the metal chassis of a machine does not become energized. Overcurrent protection devices, such as fuses and circuit breakers, automatically interrupt the flow of electricity when a current exceeds a specified threshold. These devices are designed to protect the physical circuit from overheating and causing fires, but they do not always act quickly enough to prevent a fatal shock to an individual worker. That specific human preservation role often falls to ground fault circuit interrupters, which detect minute imbalances in current and cut power in milliseconds. While permanent installation design is heavily regulated, temporary wiring, extension cords, and portable power tools introduce significant operational variability and risk into the workplace. Flexible cords are inherently more susceptible to mechanical damage than rigid conduit, making frequent inspection a critical task. You must look for physical indicators of degradation, such as frayed jacket insulation, exposed copper wires, missing grounding pins on plugs, and severe kinking. Overloading circuits by plugging multiple high-draw devices into a single extension cord or power strip creates an immediate thermal hazard. OSHA standards explicitly prohibit using temporary wiring or extension cords as a substitute for permanent facility wiring. Furthermore, handheld electropower tools must either feature a verified 3-wire grounding plug or be clearly labeled as double insulated to ensure the operator is isolated from potential internal component failures. When maintenance or servicing is required on machinery, relying solely on a control switch or a circuit breaker is insufficient to guarantee safety. We must implement rigid lockout/tagout procedures, commonly referred to as LOTO, to ensure comprehensive isolation from all energy sources. Before any worker exposes themselves to potentially live components, the specific electrical disconnect must be physically opened and secured with a personal lock and tag. This sequence prevents accidental re-energization by another employee who might be unaware that maintenance is actively occurring down the line. After applying the lock, the technician must always verify the isolation by using a calibrated voltmeter to test for the absence of voltage. Treating a system as de-energized before physically testing it is a dangerous assumption that directly leads to severe workplace fatalities. See you in the next lecture. Welcome back. Today we are going to examine the operational and legal framework surrounding personal protective equipment in the workplace. To understand the true role of personal protective equipment, we must first look at how OSHA views workplace hazard through a structured framework known as the hierarchy of controls. This system prioritizes engineering and administrative interventions over equipment worn by the worker, placing personal protective equipment at the absolute bottom of the list. Engineering controls physically modify the environment to eliminate the risk entirely, such as installing local exhaust ventilation or mechanical safeguards on machinery. Administrative controls alter the way people work by implementing rotating shifts, training protocols, or mandatory rest breaks to limit the duration of exposure. Only when these higher-level interventions prove insufficient or technologically unfeasible does personal protective equipment become necessary. It is critical to recognize that protective gear does not eliminate the hazard from the environment. It merely places a physical barrier between the hazard and the individual worker. Consequently, if the equipment fails or is worn incorrectly, the worker is left completely exposed to the danger without any secondary protection. Because it relies heavily on human behavior and constant compliance, it is considered the final and least reliable line of defense against workplace threats. Under OSHA Standard 1910.132, employers bear the primary legal responsibility to evaluate the workplace and identify potential hazards that require physical protection. This process begins with a formal hazard assessment, which is a systematic walkthrough of the facility to inspect for impact, penetration, compression, chemical, heat, harmful dust, and light radiation dangers. The employer must document this assessment through a written certification that explicitly identifies the workplace evaluated, the person conducting the evaluation, and the specific dates of the assessment. Once a hazard is identified, the employer is legally obligated to select the appropriate type of equipment that properly fits each affected employee. Furthermore, the financial burden of providing this gear falls squarely on the employer, who must purchase and provide the equipment at no cost to the employees, with very few exceptions such as non-specialty safety toe footwear. It is also the employer's duty to replace damaged or worn-out gear and to ensure that any employee-owned equipment meets strict safety standards before it is permitted on the shop floor. Defective or damaged equipment must be removed from service immediately to prevent accidental exposure and potential injury. When we look at specific body parts requiring defense, eye and face protection must conform strictly to ANSI Z87.1 standards to ensure adequate impact resistance. Safety glasses with side shields protect against flying particles, while chemical splash goggles are necessary when handling hazardous liquids that could bypass regular glasses. Face shields provide broader coverage, but must always be worn over safety glasses or goggles rather than as standalone protection. Forehead protection. Hard hats are classified into distinct types and classes depending on the nature of the industrial hazard. Type 1 hard hats are designed to reduce the force of impact resulting from blows solely to the top of the head, whereas Type 2 hard hats protect against both top and lateral impacts. From electrical perspective, Class G hats are rated for low voltage up to 2,200 volts. Class E hats handle high voltage up to 20,000 volts, and Class C hats offer no electrical protection whatsoever. Footwear must meet ASTM F2413 standards to protect against heavy falling objects, punctures, and electrical conductivity risks in specialized environments. Hand protection requires careful matching of glove material to the specific chemical or physical hazard, ensuring that a glove designed for mechanical abrasion is not mistakenly used for caustic acids. Respiratory protection introduces a highly regulated tier of safety that applies when engineering controls cannot maintain air quality above permissible exposure limits. Before an employee can wear a respirator, the employer must implement a comprehensive, written respiratory protection program detailing selection, medical evaluations, and fit testing. A medical evaluation is mandatory because respirators increase the physiological burden on the cardiovascular and pulmonary systems, meaning some individuals cannot safely wear them. Annual fit testing ensures that tight-fitting face pieces create an airtight seal on the individual's face, preventing contaminated air from leaking into the breathing zone. Workers must also be trained to perform user seal checks every single time they put the respirator on, which involves both positive and negative pressure tests. Particulate respirators use filters to trap airborne particles like dust or mist, but they offer zero protection against hazardous gases or vapors. For chemical gases, air purifying respirators require specific chemical cartridges that chemically bind the contaminants, and these cartridges must be replaced according to a strict schedule before breakthrough occurs. In atmospheres that are immediately dangerous to life or health, atmosphere-supplying respirators are required to provide clean air from an independent source. Proper usage of personal protective equipment requires regular training so that every worker understands exactly when the gear is necessary and how to properly don, doff, adjust, and wear it. Fitting is not a minor detail. Improperly fitted equipment can introduce new hazards, such as loose gloves getting caught in rotating machinery or loose straps causing trips. Maintenance and cleaning are equally vital to ensure the physical integrity of the protective materials over time. Equipment must be inspected for cracks, tears, discoloration, or signs of material degradation before every single work shift. Cleaning must follow manufacturer instructions precisely, as harsh solvents can degrade the specialized coatings on safety lenses or weaken the structural integrity of a hard hat shell. When equipment reaches the end of its service life or becomes contaminated with hazardous substances, it must be disposed of in accordance with environmental regulations rather than discarded in standard waste bins. Consistent, correct use of this equipment is completely mandatory for preventing severe injury when handling physical, chemical, or environmental threats on the job. Thank you for your time, and I will see you in the next lecture. Hello and welcome back. Managing chemical risks in the workplace requires a systematic infrastructure that eliminates guesswork and transfers critical safety parameters from chemical synthesis directly to the point of operational execution. This structural mechanism is codified by the Occupational Safety and Health Administration through the Hazard Communication Standard, which establishes a uniform architecture for identifying, documenting, and conveying chemical hazards. A cornerstone of this standard is the enforcement of a comprehensive, site-specific written hazard communication program maintained by the employer. This written protocol cannot remain a passive binder on an administrative shelf. Instead, it serves as an active operational blueprint that details precise inventory mapping, describes exactly how mandatory safety information is distributed, outlines detailed worker education protocols, and specifies safety procedures for non-routine tasks. If your operational environment introduces any chemical inputs into daily processes, understanding the exact boundaries of this regulatory framework is mathematically linked to reducing clinical injury rates and maintaining systemic compliance. To establish a truly global safety vocabulary, the current framework integrates the globally harmonized system of classification and labeling of chemicals, specifically aligning with recent updates that optimize hazard accuracy across the industrial supply chain. This integrated global system shifts the burden of chemical evaluation upstream to the technical entities who manufacture or import the chemical substances. These entities are legally required to evaluate scientific data against precise criteria to classify both physical hazards, such as flammability, explosivity, and reactivity under pressure, and health hazards, including acute toxicity, carcinogenicity, and skin corrosion. For operational workers, this structured system guarantees that regardless of the chemical origin or the manufacturing brand, the foundational indicators used to communicate risk remain perfectly consistent, predictable, and structurally decoupled from proprietary corporate terminology. The most visible components of this communication architecture are the standardized labels affixed directly to chemical containers, designed to convey severe structural risks immediately at the point of operational contact. Every compliant container label relies on a deterministic combination of structural elements, starting with specific product identifiers and a clearly assigned signal word, either danger for high-severity hazards or warning for less severe operational risks. These are accompanied by standardized hazard statements that explicitly describe the nature of the chemical risk, along with precautionary statements that outline specific preventative interventions, response protocols, storage constraints, and proper disposal methodologies. Furthermore, the label integrates geometric, diamond-shaped pictograms featuring a distinct red border and a black symbol on a white background, ensuring that critical physical and health threats are visually scannable even across varying language proficiencies or high-stress emergency scenarios. When an operational task requires deeper analytical detail than a brief container label can provide, you must immediately consult the corresponding safety data sheet, which functions as a standardized, highly structured 16-section technical manual for that specific chemical mixture. The structural integrity of the safety data sheet relies entirely on its rigid layout, ensuring that critical emergency data, such as first aid measures, firefighting tactics, and accidental release measures, are explicitly localized within the exact same early sections of every single document globally. Moving deeper into the document, later sections provide specific technical parameters regarding physical and chemical properties, detailed toxicological data, and explicit stability and reactivity metrics that explain how the material behaves under altered thermal or atmospheric conditions. Mastering the navigation of these 16 sections allows you to quickly locate precise accidental exposure limits, establish appropriate ventilation parameters, and deploy the exact engineering controls necessary to isolate a chemical threat before any physical contact occurs. Ultimately, the mechanical execution of chemical safety relies on translating these centralized documentation standards into real-world operational vigilance during your daily industrial tasks. Recognizing potential chemical exposures requires an ongoing awareness of environmental indicators, such as unexpected olfactory cues, visible atmospheric vapors, or sudden structural degradation of containment equipment. If an operation requires handling volatile or reactive materials, you're strictly entitled to full, unhindered access to the workplace chemical inventory and the associated documentation library prior to commencing any physical operations. By actively verifying container labels, reviewing personal protective specifications within the data sheets, and confirming that the handling protocols match the employer's written program, you effectively close the gap between theoretical regulatory compliance and concrete physical protection. See you in the next lecture. Leading Age +4. Hello, and welcome back. We're here to talk about something so ubiquitous that it is easy to look right past it, the very ground you stand on. In a general industry setting, walking and working surfaces represent the baseline of operational safety. It sounds simple enough to keep a floor clear, but the data tells a much more stubborn story. Slips, trips, and falls remain a primary driver of lost time injuries and structural workplace incidents across every sector, from warehouse floors to heavy manufacturing facilities. To manage this risk effectively, you must understand the underlying parameters that dictate how surfaces must be maintained, inspected, and structurally guarded under current regulatory standards. We need to move away from treating housekeeping as a superficial chore and instead view it as a critical engineering control. Let us begin with the general infrastructure requirements defined by regulatory frameworks, specifically how structural surfaces must handle environmental loads and contamination. A facility floor must have the documented structural integrity to support its maximum intended load, and these capacity ratings must be clearly posted where required. Beyond structural load, environmental conditions dictate safety. Floors must be kept in a clean, orderly, and, as far as feasible, dry condition. When your operational processes are inherently wet, such as in food processing or chemical washdown zones, you are required to maintain continuous drainage and provide dry standing areas, which typically means incorporating non-slip mats, false floors, or raised platforms. Regular inspections are not a casual recommendation. They are a continuous operational requirement. When a hazard like a loose floorboard, a deep crack, or an oil spill is identified, you must correct it before allowing personnel to access the zone again. If an immediate repair is impossible, the area must be physically isolated and guarded to prevent accidental entry. When we look at spaces where the elevation changes, the risk profile shifts dramatically, and this is where guardrail systems become mandatory. For general industry, any unprotected edge or floor opening that sits 4 feet or more above a lower level must be guarded. A standard guardrail system is a precise structural assembly, not an afterthought. The top rail must be positioned exactly 42 inches above the walking working surface, with a tolerance of plus or minus 3 inches. This rail must be structurally capable of withstanding a concentrated downward or outward force of at least 200 pounds applied within 2 inches of the top edge. Beneath the top rail, you must install a mid-rail positioned exactly halfway between the top rail and the floor, or utilize equivalent structural infill like mesh or vertical balusters spaced no more than 19 inches apart. Furthermore, To prevent tools or materials from rolling off the edge and striking workers below, you must install a toe board that is at least 3.5 inches in vertical height, with no more than a quarter-inch clearance from the floor itself. Stairways and high-traffic operational paths introduce their own precise mechanical and structural requirements. Any flight of stairs with 4 or more risers must be equipped with appropriate handrails or stair rail systems to provide continuous support. For standard stairways, the handrail height must be maintained between 30 and 38 inches, measured directly from the leading edge of the stair tread. The stairs themselves must be built to uniform dimensions. Variations in riser height or tread depth within a single flight can easily disrupt a person's natural stride and induce a trip. In heavy operational zones where forklifts and pedestrians share space, simple visibility is insufficient. You need to implement formal floor marking protocols, establishing clear, high-visibility boundaries that designate dedicated walking lanes isolated from mechanical handling hazards. This spatial segregation is particularly vital around high-risk transit areas like loading docks, where large openings are frequently exposed to changing outdoor weather conditions and heavy vehicle movements. Elevated platforms, such as catwalks, mezzanines, and fixed maintenance locations, demand identical rigor, particularly when accessed via ladders or temporary structures. For fixed ladders, recent regulatory updates have fundamentally shifted how we look at fall protection. Historically, cages were the standard mechanism for ladders exceeding 20 feet, but modern standards have changed this rule. For any fixed ladder installed or modified after late 2018 that extends more than 24 feet above a lower level, a cage is no longer considered acceptable fall protection on its own. Instead, you must implement a dedicated ladder safety system or a personal fall arrest system, which directly anchors the climber via a body harness to a carrier rail or cable. Ladders must also maintain a minimum clear width of 16 inches between side rails and provide at least 7 inches of perpendicular clearance behind the rungs to ensure proper footholds. When employees step off a ladder onto an elevated platform, grab bars or side rails must extend at least 42 inches above the landing surface to guarantee a secure transition. Managing these hazards effectively requires a shift from a reactive mindset to a proactive, systemic approach. This involves conducting routine risk assessments and physical site inspections to catch changing conditions before they cause an incident. Walkways must be kept clear of temporary obstructions like extension cords, pallets, or structural debris, which means your housekeeping protocols must be embedded directly into daily operational workflows. Every high-traffic zone, mezzanine, and loading dock must be evaluated through the lens of continuous fall protection and surface integrity. By engineering out the hazards with compliant guardrails, installing appropriate ladder safety systems, and maintaining clean, dry floor conditions, you minimize the variables that lead to unpredictable workplace accidents. I will see you in the next lecture. La Payer Stair Plus 6. Welcome back. We are shifting our focus to a critical element of operational safety that handles how a facility responds when normal operations break down entirely. An emergency action plan is a highly structured document that establishes explicit protocols for life-threatening workplace scenarios. OSHA requires this plan to be written down and readily available for employee review if an organization has more than 10 employees. Those smaller operations may communicate it orally. At its core, the plan must detail precise procedures for reporting emergencies, such as fires, chemical releases, or severe weather events. It must explicitly delineate evacuation types and assign clear, unmistakable exit routes to specific groups of employees. The document must also establish exact protocols for accounting for all personnel after an evacuation has occurred, ensuring nobody is left behind in a hazardous zone. For facilities with continuous processes, the plan must define the exact actions to be taken by individuals who remain behind to operate critical plant operations before they can safely exit. Finally, The plan must designate specific job titles or names of employees who possess the authority and information to explain duties under the plan to others. While evacuation is often the default response to a sudden hazard, certain environmental conditions require a completely different approach known as sheltering in place. This protocol is typically triggered when external atmospheric hazards, such as toxic chemical plumes or radiological releases, make stepping outside far more dangerous than staying indoors. A robust emergency action plan must define the structural areas within the facility that serve as designated safe rooms during these specific scenarios. These interior spaces should ideally have minimal windows, dense construction, and mechanical options to isolate the building's ventilation system to prevent drawing in contaminated outdoor air. Employees must be trained to recognize the distinct audible or visual signals that differentiate a shelter-in-place order from an immediate evacuation order. Managing these logistics prevents localized chaos and ensures that personnel move deliberately to the safest possible sector of the structure based on the precise nature of the threat. A logical extension of emergency planning is the fire prevention plan, which addresses the proactive mechanics of minimizing ignition risks before an evacuation becomes necessary. Just like the emergency action plan, this program must be documented in writing for facilities with more than 10 employees and made accessible for routine workforce review. The document must systematically list all major fire hazards present in the facility, ranging from accumulated wood shavings to bulk chemical storage vats. It must outline explicit handling and storage protocols for these materials, alongside a comprehensive inventory of potential ignition sources and their corresponding control systems. Crucially, the plan must prescribe clear procedures to control the hazardous accumulation of flammable or combustible waste materials, such as oily rags or discarded packaging. It must explicitly name the job titles of personnel responsible for maintaining heat-producing equipment to prevent accidental ignition and those tasked with controlling fuel source hazards. When a fire does occur, it cannot be treated as a uniform hazard, which is why fire protection standards categorize fires into distinct classes based on the fuel source involved. Class A fires involve ordinary combustible solids such as timber, paper, fabrics, and many common plastics that leave an ash residue. Class B fires are fueled by flammable or combustible liquids and gases, including petroleum greases, solvents, alcohols, and lacquers. Class C fires involve energized electrical equipment, which necessitates the utilization of non-conductive extinguishing agents to prevent lethal electrical shock to the operator. Class D fires involve highly reactive combustible metals such as magnesium, titanium, and sodium, which react violently with water and require specialized dry powder agents. Finally, Class K fires involve commercial cooking media like vegetable oils and animal fats found in high-temperature industrial kitchens. Understanding these absolute distinctions is vital because applying the wrong extinguishing agent to a specific fuel source can rapidly accelerate the fire or cause catastrophic injuries. To combat these hazards in their initial localized state, employers must manage the selection, placement, and maintenance of portable fire extinguishers across the facility floor. OSHA mandates that extinguishers for Class A hazards must be distributed such that the maximum travel distance for any employee to reach one does not exceed 75 feet. For Class B hazards, the risk profile of flammable liquids reduces that permissible travel distance to 50 feet or less, recognizing how quickly liquid fires expand. Class C equipment must be distributed based on the existing patterns for Class A or Class B hazards, ensuring non-conductive protection is always near electrical components. Employers who designate their workforce to use these devices must provide a formal educational program upon initial hire and repeat it annually thereafter. This training focuses heavily on the standard pass technique, which dictates that an operator must pull the pin, aim low at the base of the fuel source, squeeze the handle, and sweep the nozzle horizontally. The physical readiness of this fire protection equipment is maintained through a rigid hierarchy of inspection, maintenance, and structural testing schedules. Employers are legally obligated to perform a visual inspection of all portable fire extinguishers at least once every month to confirm they are in their designated locations, unblocked, and showing proper gauge pressure. Beyond these internal visual checks, each extinguisher must undergo a thorough annual maintenance check conducted by a trained technician, with the service date documented on the unit's inspection tag. Stored pressure dry chemical extinguishers that require a 12-year hydrostatic test must also be completely emptied and subjected to specific internal maintenance procedures every 6 years. Hydrostatic testing, which pressure tests the structural integrity of the extinguisher cylinder using a liquid medium, must be performed at strict intervals, typically every 5 years for carbon dioxide or water units, and every 12 years for dry chemical mild steel shells. Missing these maintenance windows compromises equipment reliability, transforming a critical safety asset into a non-functional liability when a fire breaks out. See you in the next lecture. OSHA +9. Hello, and welcome back. We are here to talk about a force that is as pervasive as it is dangerous when misunderstood. Electricity drives our industrial infrastructure, but it requires a disciplined framework of control to prevent catastrophic failure. Our goal is to dissect how electrical energy behaves maliciously in a workplace environment and how we can systematically eliminate the risks associated with it. We will look at this through the lens of objective physics and established regulatory constraints. It is not a matter of luck. It is a matter of understanding system boundaries and ensuring they are maintained. To understand electrical hazards, we must first look at the 3 primary ways electricity causes physical trauma to the human body. Electrocution occurs when a lethal amount of current passes through the body, disrupting the nervous system and stopping the heart. Electrical burns are the physical destruction of tissue caused by the heat generated from current flowing through resistance, which frequently happens at the point of contact. An arc flash, however, is a sudden release of electrical energy through the air when a high voltage gap exists and insulation breaks down between conductors. This creates a plasma explosion that can exceed 35,000 degrees Fahrenheit, vaporizing metal and causing severe thermal radiation injuries without a worker even touching the equipment. Electrical failures rarely happen without a systemic breakdown in equipment integrity or operational discipline. Improper wiring, such as overloaded circuits or unapproved modifications, forces components to operate beyond their rated capacities, which leads to catastrophic overheating. Damaged insulation on power cords and internal wiring exposes energized conductors, turning everyday actions into potential contact points. The misuse of tools, such as using non-insulated hand tools near live circuits or pushing a device past its duty cycle, bypasses built-in design safeguards. When these physical anomalies combine with damp or hazardous environmental conditions, the risk of a ground fault or a short circuit escalates significantly. Employers bear the legal and structural responsibility under federal regulations to maintain electrical installations in a safe operational state. This mandate requires an active maintenance program to ensure that overcurrent protection devices, like circuit breakers and fuses, operate within their specified clearing times. Grounding is a non-negotiable requirement that provides a safe, low-resistance path for fault current to travel back to the source, which trips the breaker rather than routing through a human operator. Furthermore, employers must install and maintain protective devices like ground fault circuit interrupters, which continuously monitor current balance and disconnect power within milliseconds if an imbalance occurs. We cannot talk about maintenance without addressing the strict enforcement of lockout/tagout procedures, which serve as the primary mechanism for isolating hazardous energy. A common and dangerous myth is that turning off a switch means a system is safe to work on. Under current regulatory frameworks, equipment is treated as fully energized until an electrically safe work condition is explicitly verified. This verification process itself is considered energized work, meaning that qualified workers must wear appropriate arc-rated personal protective equipment while applying locks, verifying blade positions, and testing for the absence of voltage. Only when every single source of electrical and stored non-electrical energy is isolated, locked, and verified by zero-voltage testing is the environment safe. See you in the next lecture. The Electricity Forum plus 2 additional safety overview to see how these concepts are visually presented in a field environment. You can watch the Avoid Electrical Hazards Construction Safety Training OSHA Outreach Courses video, which demonstrates the practical inspection of cords, plugs, and tools to ensure your equipment satisfies basic regulatory standards. Welcome back. In this session, we turn our attention to personal protective equipment, which represents a critical element of workplace safety despite being the final line of defense against occupational hazards. To understand the role of personal protective equipment, we must first look at how safety professionals prioritize hazard control. The hierarchy of controls dictates that we should always attempt to eliminate a hazard entirely, substitute it with a safer alternative, or implement engineering or administrative controls before relying on equipment worn by the worker. Personal protective equipment does not remove the hazard from the environment. It merely places a physical barrier between the worker and the danger. If that barrier fails, or if a worker chooses not to wear it, the exposure occurs immediately. This inherent limitation is why OSHA considers personal protective equipment a supplementary control strategy rather than a primary solution. Workers must remain aware that wearing protection does not make an environment safe, but rather mitigates the risk of an environment that remains fundamentally hazardous. Relying solely on this final barrier requires strict adherence to usage protocols and a clear understanding of what the equipment can and cannot do. Protecting the head requires an understanding of the specific categories of protective helmets, commonly known as hard hats, which are classified by both the type of impact they resist and their electrical performance. Type 1 hard hats are engineered exclusively to reduce the force of impacts resulting from blows solely to the top of the head, whereas Type 2 hard hats provide additional protection against lateral impacts that may strike the sides, front, or back of the shell. Beyond mechanical impact, these helmets are rated for electrical insulation under 3 distinct classes. Class G, or general helmets, provide limited voltage protection up to 2,000 volts, while Class E, or electrical helmets, are tested to withstand up to 20,000 volts to protect against high-voltage conductors. Class C, or conductive helmets, offer zero electrical protection and are intended only for situations where impact hazards exist but electrical dangers are completely absent. Employers must ensure that the hard hat selected matches the precise profile of the workplace hazards identified during the mandatory hazard assessment. Eye and face protection must match the specific physical state of the contaminant, whether it takes the form of flying particles, chemical splashes, or harmful light radiation. Standard safety glasses with side shields offer baseline protection against frontal and angular impact from solid debris, but they are insufficient when dealing with liquid chemical splashes or heavy dust concentrations. In environments where corrosive liquids or vapor hazards are present, workers must utilize chemical splash goggles, which form a tight, continuous seal around the orbital area of the face to prevent fluids from seeping behind the lens. When the hazard involves severe splashing, flying fragments, or intense heat, a face shield must be worn in conjunction with, and never as a substitute for, primary eye protection like safety glasses or goggles. For tasks involving welding or cutting, lenses must incorporate specific filter shades that attenuate harmful ultraviolet and infrared radiation to prevent permanent ocular damage. Proper fitting is essential to ensure that the equipment remains secure during movement without causing pressure points that discourage consistent usage. Hand and foot protection require careful material selection because a glove or boot that excels in one scenario may fail catastrophically in another. Hand protection ranges from heavy-duty leather gloves designed to resist abrasions and cuts to specialized polymer gloves that resist specific chemical permeation. For chemical handling, safety managers must consult chemical resistance guides to determine the breakthrough time of a glove material, as a material like latex might degrade rapidly when exposed to petroleum-based solvents. Foot protection involves safety shoes or boots equipped with impact-resistant toe caps, which must meet specific compression and impact standards to protect against falling objects. Depending on the environment, these boots may also require puncture-resistant soles, metatarsal guards, or specialized outsoles designed to resist electrical conduction or chemical degradation. Daily inspection of both hand and foot gear is necessary to detect signs of wear, such as thinning material, cracks, tears, or separation of seams, which immediately compromise the protective qualities of the item. Respiratory defense introduces a higher level of complexity because selecting the wrong equipment can lead to acute toxicity or long-term systemic health complications. Respirators are broadly categorized into air-purifying respirators, which filter contaminants out of the ambient air, and atmosphere-supplying respirators, which provide a clean source of breathing air from an independent supply. Air-purifying respirators can use particulate filters, gas cartridges, or a combination of both, but they are entirely useless in oxygen-deficient environments containing less than 19.5% oxygen by volume. Before any worker can use a tight-fitting respirator, they must undergo a formal medical evaluation to ensure their cardiovascular and respiratory systems can handle the increased physiological workload of breathing through a filter. Furthermore, a mandatory fit test must be performed annually to verify that the respirator mask forms an airtight seal against the face, as even minor facial hair or structural variations can cause dangerous inward leakage of contaminated air. Maintaining personal protective equipment requires a disciplined regimen of daily inspections, proper cleaning, and climate-controlled storage to prevent premature degradation of the materials. Workers must inspect their equipment before every shift, looking for brittle plastics, frayed straps, compromised seals, or any signs of chemical attack. Cleaning must follow manufacturer guidelines precisely, using mild soap and water rather than harsh solvents that could dissolve protective coatings or weaken structural integrity. Storage conditions must protect the equipment from direct sunlight, extreme temperatures, moisture, and mechanical damage, as leaving safety gear in the bed of a truck or a damp locker will significantly accelerate material breakdown. When an inspection reveals any defect, or if an item has sustained an impact or chemical exposure it was designed to absorb, the equipment must be removed from service immediately and destroyed to prevent accidental reuse. Adhering to these standards ensures that when the final barrier is called upon, it performs exactly as intended. That covers the core principles of personal protective equipment selection and maintenance. So I will see you in the next lecture. Welcome back. We are shifting our focus to a regulatory framework that underpins almost every operational scenario you will encounter in an industrial environment, specifically the management of hazardous substances. The goal here is not merely to satisfy a legal mandate, but to establish an engineering-like predictability regarding how chemical risks are identified, contained, and communicated across your facility. The foundation of this system relies on a structural taxonomy divided strictly between physical hazards and health hazards. Physical hazards describe the intrinsic mechanical or energetic behavior of substance under specific environmental conditions, such as its propensity to ignite, explode, react destructively with other materials, or rapidly expand under pressure. Health hazards, conversely, quantify the biological impact that the material exerts on a human organism upon exposure, encompassing immediate acute toxicities like systemic poisoning or chemical burns alongside insidious chronic risks like carcinogenicity, mutagenic alterations, or target organ degradation over prolonged timelines. Understanding this fundamental distinction changes how you approach containment and emergency mitigation, as a flammable liquid demands rigorous ignition source isolation, while a severe respiratory sensitizer dictates engineered local exhaust ventilation. To ensure that these distinct classifications are uniformly translated from chemical synthesis laboratories down to the factory floor, the regulatory architecture dictates a standardized artifact known as the safety data sheet. This is a highly structured, non-negotiable 16-section document designed to eliminate ambiguity by placing critical technical data in predictable locations. Sections 1 through 8 serve as the immediate operational interface, providing rapid access guidance on substance identification, explicit hazard declarations, essential first aid protocols, specialized firefighting methodologies, accidental release containment strategies, and safe handling metrics. Sections 9 through 11, along with Section 16, transition into dense empirical and scientific parameters, detailing exact physical and chemical properties, stability vectors, reactivity risks, and comprehensive toxicological data derived from controlled research exposures. While the safety data sheet acts as the comprehensive reference repository, the point-of-use communication is handled by standardized container labeling requirements that provide immediate visual telemetry to an operator. Every compliant shipping or transfer container must feature distinct mandatory elements, starting with a clear product identifier and an explicit signal word, either danger for severe risks or warning for less severe hazards, to establish an immediate hierarchy of threat. Accompanying these words are explicit hazard statements describing the nature of the risk and prescriptive precautionary statements outlining the exact defensive measures, storage limitations, and disposal constraints mandated for that chemical class. Furthermore, the label incorporates standardized graphic symbols enclosed in red diamond borders, which visually index specific hazard profiles such as corrosion, acute toxicity, or oxidizing potential, ensuring that language barriers or rapid operational paces do not degrade situational awareness. Deploying these tools effectively requires the formal codification of a written hazard communication program, which functions as the architectural blueprint for chemical safety management within any operational boundary. This written document cannot be a generic template. It must accurately inventory every single hazardous chemical present on the site and cross-reference them directly to the accessible repository of current safety data sheets. The program must formally define the specific protocols for maintaining and updating this inventory, explain the precise labeling methods utilized for secondary internal transfer containers, and detail the exact procedures for managing non-routine operational tasks or contractor communication. Ultimately, this program provides the definitive operational governance structure that ensures safety data remains continuously accurate and verifiable even as your facility alters its manufacturing processes or introduces new materials. The absolute point of failure for any written safety program is the human interface, which is why comprehensive employee training serves as the critical connective tissue of the entire framework. Training protocols must verify that every operator can intuitively interpret the standardized labels, navigate the 16-section layout of a safety data sheet to locate medical treatment data during an emergency, and correctly execute the specific procedural controls designed for their daily tasks. This educational process must occur prior to an employee's initial assignment to any area containing hazardous substances and must be repeated comprehensively whenever a completely new chemical hazard or classification is introduced into their workspace. By prioritizing this objective, empirical verification of worker competency, you systematically reduce the margin for human error, ensuring that dangerous chemical exposures and volatile industrial incidents are mitigated before they can manifest on the shop floor. See you in the next lecture. This breaks down the essential 16-section document format and employee accessibility rules discussed in this lesson. Welcome back. Let us take a structured look at how we safely manage the physical movement and storage of raw resources and finished products. Every logistical operation relies on moving items from one point to another, but doing so without structural discipline introduces severe operational risks. When we analyze workplace injuries, an incredibly high percentage stems directly from poor material handling practices. The human body is highly resilient, yet it has distinct structural limits that cannot be bypassed without consequence. If you look at standard general industry environments, musculoskeletal disorders represent a massive burden on both organizational productivity and individual well-being. These injuries rarely happen because of a single catastrophic event, but rather accumulate through repetitive, mechanically inefficient movements. By focusing on ergonomic principles, we can systematically eliminate the root causes of strain. The most basic rule of thumb is to design the workflow so that workers do not have to lift from the floor or reach above their shoulders. Keeping loads close to the body's center of gravity drastically reduces the mechanical leverage exerted on the lower back, particularly the lumbar spine. Manual lifting is only one side of the coin, as industrial spaces routinely rely on heavy mechanical equipment to achieve necessary throughput. Mechanical handling brings massive force into the workspace, meaning that any failure in control can quickly become fatal. Forklifts or powered industrial trucks are indispensable tool sets in modern warehouses, but they require strict compliance with load limits and behavioral bounds. A forklift has a variable center of gravity that forms a stability triangle between its wheels, and overloading or turning too fast can easily cause a dynamic tip over. OSHA requires that operators are not just familiar with the controls, but specifically trained and certified to understand how weight distribution changes during high-tier placements. Similarly, automated conveyors present mechanical hazards like pinch points, rotating shafts, and wrap points that can easily trap hair, clothing, or limbs. Engineering controls, such as mechanical guards and emergency pull cords, must be installed and verified before every shift to ensure that a mechanical failure or human slip does not lead to a crushing injury. Once materials arrive at their destination, how they are stored dictates the overall safety of the working environment. Overcrowded storage areas are an open invitation to accidents, as they restrict visibility and impede the safe movement of pedestrian traffic and handling vehicles. According to general industry standards, permanent aisles and passageways must be kept completely clear of obstructions and appropriately marked with visible boundaries. Furthermore, storage spaces require precise housekeeping to prevent fire hazards, pest harborage, or tripping risks from accumulating. One critical dimension that people often overlook is fire suppression clearance. OSHA regulations mandate that a continuous horizontal plane of at least 18 inches of clearance must be maintained below all automatic sprinkler heads. If you stack pallets or material bundles into this zone, you disrupt the spray pattern of the system, rendering it ineffective during a fire event. Security in storage means ensuring that nothing can slide, tip, or collapse unexpectedly under the influence of gravity. To systematically prevent falling objects, we must follow strict, formalized procedures when stacking different material profiles. When handling materials like boxed items or loose bundles, the units must be bound, cross-dyed, or securely shrink-wrapped to form a singular, stable mass. For specialized materials, specific height and geometry constraints apply to ensure structural stability. Manual handling of lumber, for instance, is limited to a maximum stack height of 16 feet, whereas forklift-assisted stacking can extend to 20 feet, provided the foundation is level and solidly supported. Bag materials require a specific step-back geometry where you taper the layers and cross-key the bags at least every 10 rows high to prevent a localized shift from triggering a massive slide. Cylindrical objects such as metal pipes, structural steel, or heavy poles present unique rolling hazards that must be mitigated immediately upon placement. Unless these items are nested within dedicated structural racks, they must be securely blocked and chalked on both sides of the bottom tier to prevent spreading or tilting. Proper material management also demands that we account for the final stage of the operational life cycle, which involves the systematic disposal of waste materials. Debris, scrap metals, and discarded packaging cannot simply be allowed to pool in working zones or exit paths, as they create immediate compliance violations and safety risks. When disposing of materials from upper levels, chutes, or enclosed drop zones must be utilized to isolate the falling mass from anyone working below. Waste management is fundamentally an extension of housekeeping. A clean floor surface ensures that the coefficient of friction remains predictable for both footwear and vehicles. By integrating strict weight tracking, equipment inspection checklists, and deliberate stacking strategies into daily routines, you protect your team from crushing hazards and sudden mechanical failures. Safety in logistics is ultimately an optimization problem where we balance mechanical capacity against physical layout constraints. See you in the next lecture. SkillCat +7. Hello, and welcome back to our series on operational safety protocols. When we look at industrial machinery, we are looking at equipment designed to manipulate materials with immense force, speed, and precision. This inherent power creates severe risks for anyone operating or working near these systems, specifically related to the point of operation, power transmission apparatuses, and other moving parts. The point of operation is the specific location on a machine where work is actually performed on the material, such as cutting, shaping, boring, or forming. Power transmission parts include flywheels, pulleys, belts, connecting rods, couplings, cams, spindles, chains, cranks, and gears that transmit energy to the part of the machine performing the work. Beyond these primary areas, moving parts can include reciprocating, rotating, and transverse moving parts, as well as feed mechanisms and auxiliary parts of the machine. Any machine part, function, or process which may cause injury must be safeguarded to prevent hazards such as nipping, shearing, punching, or catching. Failing to secure these areas directly exposes workers to severe physical trauma, making a comprehensive understanding of barrier requirements a fundamental aspect of general industry compliance. To systematically mitigate these risks, OSHA outlines strict technical requirements for different classifications of machine guards, each operating on a distinct mechanical principle. Fixed guards are permanent components of the machine that do not depend on moving parts to perform their function. They're typically constructed of sheet metal, screen, wire cloth, or bars, and are securely fastened to the frame using fasteners that require specific tools for removal. Interlock guards are designed to be connected to the machine's power or control system, so that when the guard is opened or removed, the tripping mechanism automatically shuts off or disengages the power, preventing the machine from operating until the guard is replaced. Adjustable guards are useful because they accommodate varying sizes of stock material, allowing the operator to manually position the barrier to minimize exposure to the danger zone during a specific operation. Self-adjusting guards differ because they are pushed open by the movement of the material itself, automatically expanding just enough to let the stock pass, and then returning to the closed position once the operation is complete. Each of these barriers serves to prevent the operator's hands or body parts from entering the hazardous zone during the operating cycle. Recognizing when a guard is mandatory requires a careful evaluation of the mechanical actions that take place during operation, specifically focusing on rotating, reciprocating, and transversing motions. Rotating motion, even at slow speeds, can catch clothing, hair, or skin, pulling a worker's limb into the mechanism, with rotating shafts being particularly dangerous if they possess keys, bolts, or slots. In-running nip points are a specialized type of rotating hazard created by the rotation of parallel rolls, intersecting gears, or the contact point between a belt and a pulley. Reciprocating motion involves an up and down or back and forth movement that can trap a worker between a moving part and a fixed object, while transversing motion involves movement in a continuous straight line that creates a hazard where the moving belt or chain approaches a stationary component. Furthermore, many industrial processes generate flying debris, sparks, or toxic splashing fluids, meaning guards must also function as containment structures. Protecting against these hazards prevents struck by and caught in injuries, which represent a significant percentage of preventable industrial accidents. Maintaining these safeguards requires a structured routine of inspection and strict adherence to a zero-tolerance policy regarding tampering or unauthorized removal. Operators must visually and physically verify that all guards are securely in place and functioning as intended before initiating any production cycle. If an inspection reveals a guard that is loose, damaged, bypassed, or missing, the operator must immediately halt work and follow the established company procedure for reporting defective equipment to maintenance personnel or safety managers. Modifying a guard to bypass an interlock or removing a barrier to speed up material feeding is a major safety violation that dramatically elevates the risk of amputation or death. Safeguards must never be defeated for convenience, and any maintenance or adjustment that requires the temporary removal of a guard must be performed only under authorized lockout and tagout conditions. Ensuring that guards remain functional and unaltered is a shared operational responsibility that maintains the barrier between human tissue and destructive mechanical forces. Thanks for your time, and I will see you in the next lecture. Hello and welcome back. We are shifting our focus toward a discipline that deals with risks that are often invisible but deeply impactful over time. Industrial hygiene is the science and art devoted to the anticipation, recognition, evaluation, and control of environmental factors or stressors arising in or from the workplace. While safety engineering often addresses immediate, acute events like falls or machine injuries, industrial hygiene focuses predominantly on preventing chronic illnesses and long-term health degradation. To effectively protect a workforce, an organization cannot merely react to illnesses after they manifest. It must establish a systematic approach to identify these hidden hazards early. Anticipation involves studying workplace designs, processes, and raw materials before they are even introduced to predict what hazards might arise. Recognition follows as the active identification of existing stressors through comprehensive worksite analyses, employee interviews, and routine walkthrough inspections. Once a stressor is recognized, evaluation quantifies the magnitude of the hazard using scientific measurement and comparison against regulatory limits. Finally, control processes are established to eliminate or sufficiently mitigate the hazard, ensuring the working environment remains hospitable to human health over a multi-decade career. Occupational stressors generally fall into distinct categories, with chemical, physical, and biological vectors representing the primary threats to physiological well-being. Chemical stressors exist in various physical states, including airborne vapors, gases, mists, dusts, and fumes, which can enter the human body through inhalation, dermal absorption, or accidental ingestion. Physical stressors, on the other hand, represent environmental energies that can damage human tissue over brief or prolonged exposures. Excessive noise levels can destroy microscopic hair cells in the inner ear, leading to irreversible noise-induced hearing loss. Extreme temperatures challenge the body's thermoregulatory mechanisms, where cold stress can cause hypothermia or frostbite, and heat stress can rapidly escalate from heat exhaustion to life-threatening heat stroke. Radiation is another pervasive physical stressor, split between ionizing types like X-rays that mutate cellular structures and non-ionizing types like ultraviolet light or infrared radiation. Biological stressors include pathogenic microorganisms such as bacteria, viruses, and fungi that can cause acute infections or chronic systemic diseases when workers are exposed via contaminated fluids, surfaces, or airborne vectors. To determine whether an environmental stressor poses an actionable threat, an organization must implement rigorous exposure monitoring programs. Industrial hygienists utilize specialized instrumentation, such as personal sampling pumps, passive badges, and direct reading instruments, to measure exact contaminant concentrations in a worker's breathing zone. These collected data points are then evaluated against established regulatory benchmarks, most notably OSHA's permissible exposure limits, which are legally binding thresholds usually calculated as an 8-hour time-weighted average. Many substances also have an action level, which is typically set at half of the permissible exposure limit and serves as a regulatory trigger for increased monitoring and medical tracking. When exposure levels exceed these defined boundaries, employers are legally obligated to take corrective action to reduce the risk. Relying on casual observation or subjective employee feedback is fundamentally insufficient because many hazardous vapors are odorless, and physical stressors like radiation cannot be detected by human senses until cellular damage has already occurred. Systematic monitoring provides the empirical baseline necessary to validate whether the structural integrity of your safety management system is actually holding up under operational conditions. When monitoring reveals that exposure levels are unacceptable, the organization must apply mitigation strategies dictated by the strict hierarchy of controls. Engineering controls are fundamentally preferred because they modify the physical environment to isolate the worker from the hazard or remove the stressor at its source. This can be achieved through substitution, such as replacing a highly toxic chemical solvent with a water-based alternative, or through structural installations like local exhaust ventilation systems that capture harmful fumes before they disperse. Enclosing a noisy air compressor inside a sound dampening structure is another classic example of an engineering control that effectively alters the physical workspace. When engineering solutions are technically unfeasible or are in the process of being designed and installed, administrative controls must be deployed to alter how the work is organized. Administrative interventions do not change the physical hazard itself. Instead, they reduce worker exposure by adjusting schedules, mandating job rotations, and restricting access to high-risk zones. For instance, rotating 4 employees through a high-heat environment ensures that no single individual exceeds their physiological threshold during an 8-hour shift. While engineering and administrative measures are vital, a robust industrial hygiene program must also incorporate a structured medical surveillance program to act as a secondary defensive baseline. Medical surveillance involves a systematic protocol of targeted medical examinations, biological monitoring, and diagnostic tests tailored specifically to the unique hazards present in the facility. These medical screenings are designed to detect the earliest subclinical signs of occupational disease before the worker experiences debilitating symptoms or permanent functional impairment. For example, workers routinely exposed to high noise levels undergo annual audiometric testing to track subtle shifts in hearing thresholds over time. Similarly, individuals working around specific chemical hazards might provide blood or urine samples to measure biological exposure indices, ensuring that internal contaminant levels remain safe. A medical surveillance program also establishes essential baseline health profiles during pre-employment screenings, allowing the organization to distinguish between pre-existing conditions and new, occupationally induced health changes. This clinical data loop provides ultimate verification regarding whether your environmental engineering controls and administrative rotations are truly effective at preserving human health. See you in the next lecture. U.S. Compliance +7. Hello and welcome back. We are shifting our focus to a critical aspect of industrial hygiene that applies to anyone who might encounter biological hazards during their routine work or while responding to a workplace emergency. Bloodborne pathogens are pathogenic microorganisms that are present in human blood and can cause disease in humans. While blood is the primary vehicle, OSHA regulations also cover other potentially infectious materials, often referred to as OPIM. This category includes semen, vaginal secretions, cerebrospinal fluid, synovial fluid, pleural fluid, and any body fluid that is visibly contaminated with blood. In a general industry setting, exposure typically happens during accident response, machinery maintenance where sharp edges are present, or during janitorial operations. Understanding what we are protecting ourselves against is the first step in implementing effective controls. The three most significant threats in this category are the human immunodeficiency virus, hepatitis B, and hepatitis C. Each of these viruses affects the body differently, and they vary significantly in their durability outside the human host and their ease of transmission. The human immunodeficiency virus, or HIV, attacks the body's immune system, specifically the T cells, which helps the body fight infections. Unlike some other viruses, the human body cannot get rid of HIV completely, meaning that once an individual contracts it, they have it for life. In the workplace, the risk of transmission is generally lower compared to hepatitis viruses, but the severity of the long-term health outcomes makes strict adherence to safety protocols vital. Hepatitis B is a serious liver infection caused by the hepatitis B virus, which can lead to a chronic infection and significantly increases the risk of liver failure, liver cancer, or cirrhosis. A key differentiator for hepatitis B is its resilience, as the virus can survive in dry blood on surfaces for up to 7 days, making delayed decontamination a major hazard. Hepatitis C is another liver infection caused by the hepatitis C virus, which today is one of the most common bloodborne infections in the United States. A major challenge with hepatitis C is that many infected individuals remain asymptomatic for decades, meaning a person could spread the virus without knowing they carry it. For a bloodborne pathogen to cause an infection, it must find a mode of transmission into your bloodstream. This typically happens through a percutaneous injury, which means the skin is punctured by a contaminated sharp object like a needle, broken glass, or sharp metal fragments. Transmission can also occur when infected blood or OPIM comes into contact with non-intact skin, such as open wounds, cuts, scratches, abrasions, or active rashes. Additionally, mucous membranes line your eyes, nose, and mouth, and if contaminated fluid splashes into these areas, the virus can enter the body. It is important to note that bloodborne pathogens are not transmitted through casual contact, coughing, sneezing, or sharing food and drink. Because you cannot visually determine if a fluid contains a virus, OSHA requires the use of universal precautions. This is a system of infection control where all human blood and certain human body fluids are treated as if they are known to be infectious for HIV, HBV, HCV, and other bloodborne pathogens. Employers are required to establish a written exposure control plan if their employees have a reasonable anticipation of occupational exposure to blood or OPIM. This plan is a foundational document that must be reviewed and updated at least annually to reflect changes in technology that eliminate or reduce exposure. The plan must include an exposure determination, which identifies job classifications and tasks where occupational exposure occurs without regard to the use of personal protective equipment. It also details the schedule and methods for implementing specific sections of the standard, such as vaccination programs, post-exposure evaluation, and follow-up procedures. Employees must have seamless access to this written document so they understand the specific protocols established for their exact work environment. When an exposure incident occurs, meaning blood or OPIM contact an employee's eyes, mouth, other mucous membranes, non-intact skin, or punctures the skin, immediate medical evaluation and confidential follow-up are mandated by law. To control these risks, OSHA enforces a hierarchy of controls, starting with engineering controls that isolate or remove the bloodborne pathogens hazard from the workplace. A primary example of an engineering control in industrial settings is the mandatory use of approved sharps disposal containers. These containers must be puncture-resistant, labeled or color-coded appropriately, leak-proof on the sides and bottom, and closed prior to removal or replacement to prevent spillage. They must be placed as close as feasible to the immediate area where sharps are used or can be reasonably anticipated to be found. Work practice controls are also critical, altering the manner in which a task is performed to reduce the likelihood of exposure. For instance, employees are strictly prohibited from shearing or breaking contaminated needles, recapping them using a two-handed technique, or reaching blindly into containers where sharp objects might be hiding. Hand washing facilities must be readily accessible, and workers must wash their hands immediately or as soon as feasible after removing gloves or other personal protective equipment. When engineering and work practice controls cannot completely eliminate exposure, personal protective equipment serves as the necessary barrier between the worker and the infectious material. The employer must provide appropriate PPE at no cost to the employee, ensuring it is clean, properly maintained, and fits correctly. This equipment commonly includes disposable gloves, which should be made of nitrile or latex, and must be replaced immediately if they are torn, punctured, or compromised in any way. If there is a risk of splashing or spraying of blood, workers must wear masks, eye protection such as goggles or glasses with side shields, and face shield to protect mucous membranes. Gowns, aprons, or clinic jackets may also be necessary, depending on the volume of fluid anticipated during the task. It is a strict violation to wear contaminated PP into clean areas, such as lunchrooms or restrooms, and all gear must be removed before leaving the work area and placed in a designated container for disposal or laundering. Proper cleanup and decontamination procedures are the final line of defense to ensure a contaminated work area is made safe for general operations. All equipment and environmental or working surfaces must be cleaned and decontaminated after contact with blood or other potentially infectious materials. The decontamination process requires using an appropriate disinfectant, such as a freshly mixed solution of household bleach diluted with water at a ratio between 1:10 and 1:100, or an EPA-registered antimicrobial product. Workers performing the cleanup must wear the prescribed PP and use mechanical means like tongs, forceps, or a broom and dustpan to clean up broken glass, never using their bare or gloved hands directly. Any contaminated waste, including towels, rags, and absorbent materials saturated with liquid or semi-liquid blood, must be placed in biohazard bags that are clearly marked with a universal biohazard symbol or colored red. Regular trash cans cannot be used for biohazardous waste, as this endangers waste management personnel downstream who are unaware of the biological risk. That covers the core principles of bloodborne pathogens safety and the primary methods used to prevent transmission in industrial environments. See you in the next lecture. Hello, and welcome back. We are here to talk about a design challenge that affects every single physical workspace you will ever encounter. It is easy to think of workplace safety exclusively in terms of acute, catastrophic events like electrical shocks, fires, or catastrophic falls from heights. Yet, there's another category of injury that does not happen all at once, but rather accumulates silently over months and years of daily operation. This is where the science of ergonomics enters the picture, which is fundamentally the practice of fitting the job requirements to the physical capabilities of the human body, rather than forcing the human body to adapt to a poorly designed machine or process. When we ignore this alignment, the friction manifests as musculoskeletal disorders, which are injuries affecting muscles, nerves, tendons, ligaments, and spinal discs. These conditions include debilitating ailments like carpal tunnel syndrome, chronic lower back issues, rotator cuff tears, and repetitive motion strains. Statistics from the Bureau of Labor Statistics show that musculoskeletal disorders consistently account for a massive percentage of all lost time work injuries across general industry, illustrating that this is not a minor comfort issue, but a severe operational risk. To design a safer work system, we must first learn to identify the specific variables that introduce physical stress into an environment. The first major risk factor is awkward posture, which occurs anytime a task forces a worker out of a neutral, relaxed position. Neutral posture means keeping the joints aligned, the spine naturally curved, and the limbs close to the body, whereas bending at the waist, twisting the torso, or reaching overhead forces muscles to work at mechanical disadvantage. The second risk factor is excessive force, which refers to the physical effort required to lift, push, pull, or carry heavy objects, or to operate stiff mechanical controls. When a worker must exert high levels of muscular force, the risk of tissue deformation or sudden strain rises sharply. The third risk factor is high repetition, where the same motion is performed continuously without variation, which rapidly depletes the body's natural lubrication and healing cycles. Finally, we must consider localized or whole body vibration, which frequently occurs when operating handheld power tools or driving industrial vehicles like forklifts. Vibration disrupts normal blood flow, numbs nerve endings, and accelerates mechanical wear on joints and vascular structures. When we look for solutions to these risks, we must follow the standard industrial hygiene framework, prioritizing engineering controls that physically alter the workspace before relying on administrative behaviors. Workstation adjustability is an excellent example of an engineering control because it allows a single manufacturing line or assembly desk to accommodate workers of different heights and reaches. By incorporating height-adjustable surfaces, scissor lifts, and articulating tool arms, we ensure that a shorter employee does not have to stretch excessively, and a taller employee does not have to slouch. Furthermore, tools can be selected or redesigned with contoured handles and counterbalances to minimize the grip force required to operate them. In logistics and material handling environments, installing vacuum hoists, conveyors, or mechanical lift tables removes the raw physical force requirement completely from the human operator. The ultimate objective of these structural interventions is to keep the worker operating within their optimal functional zone throughout the entire work shift. Where engineering controls cannot completely eliminate a physical hazard, we must deploy administrative controls to manage the remaining operational exposure. Implementing proper manual lifting techniques is a fundamental administrative practice, teaching workers to bend at the knees, keep the load securely against the chest, and avoid any twisting motions while carrying a heavy weight. Another highly effective procedural tool is the job rotation schedule, which intentionally moves workers between different tasks that utilize completely distinct muscle groups. For instance, rotating an operator from a highly repetitive fine motor assembly task to a gross motor packaging task gives the fatigued hand tissues a chance to rest and recover. We must also establish structured recovery protocols, which include incorporating regular micro breaks into the production schedule to alleviate static muscle loading. A brief period of movement or stretching every 30 minutes resets the muscle fatigue clock, dramatically lowering the cumulative strain that leads to chronic occupational illness. See you in the next lecture. Qualitize +5. Welcome back. Today we are going to look at the architectural underpinnings of workplace security, specifically how to establish a robust environment that actively prevents and mitigates workplace violence. To design an effective prevention strategy, we must first learn to identify the early telemetry of aggressive behavior, as early intervention prevents minor friction from escalating into major safety breaches. Employees often exhibit observable changes before an incident occurs, such as sudden shifts in attendance patterns, uncharacteristic performance drops, or a distinct increase in arguments with peers. More severe indicators include direct verbal threats, an unhealthy obsession with weapons, or expressions of extreme desperation regarding personal or financial matters. It is an error to dismiss these signs as mere personality quirks or temporary bad moods. When these indicators present themselves, they must be registered as systemic warnings that require immediate attention from supervisory teams. Ignoring these initial behavioral anomalies allows the risk level to compound unnecessarily within the organization. We must also recognize that external hazards can breach our perimeter, which brings us to the significant impact that domestic violence has on the physical workplace. A hostile relationship at home does not neatly stop at the property line. Abusers frequently use the predictability of an employee's work schedule to commit acts of harassment or physical assault. This dynamic introduces severe vulnerability to the target employee and presents a direct threat to bystanders, clients, and co-workers in the immediate vicinity. A modern security protocol should actively encourage employees to report if they possess restraining orders or fear for their safety at work. When management is aware of these situations, they can introduce targeted engineering controls, such as altering the employee's work schedule, reassigning their workspace to a secure location, or notifying building security officers to deny unauthorized visitors entry. When a tense situation manifests in real time, personnel must be equipped with concrete, actionable strategies for verbal de-escalation to defuse the immediate threat. The foundational principle here is to deliberately lower the emotional energy of the interaction by maintaining a calm, steady vocal tone and non-threatening body language. You should avoid crossed arms, intense eye contact, or sudden physical movements that the aggressive individual could interpret as a defensive or confrontational posture. Listen actively without interrupting. Validate the individual's frustration without making unrealistic promises, and explicitly establish clear physical boundaries by maintaining a safe distance. Never challenge an angry person, command them to calm down, or trap them in an enclosed space with no clear path to exit. The ultimate objective of verbal de-escalation is not to win an argument, but to safely reduce volatility until security personnel or local law enforcement can intervene. A successful prevention program relies entirely on the implementation of transparent, frictionless reporting procedures that allow employees to flag concerning behaviors without fear of retaliation. If workers believe that speaking up will lead to professional penalties or administrative indifference, they will remain silent, creating a dangerous visibility gap in your safety infrastructure. A well-designed policy must clearly delineate exactly how to report an incident, who receives that data, and how the subsequent investigation will be handled securely. Management must treat every reported threat with absolute seriousness, ensuring that documentation is kept standardized and confidential to protect all involved parties. This reporting pipeline functions as our primary diagnostic tool, allowing safety committees to identify evolving security hazards and apply corrective controls long before an act of violence occurs. In tandem with reporting pipelines, facilities must maintain a highly detailed emergency response plan specifically optimized for hostile incidents, including active shooter scenarios. This specialized document must clearly outline the exact sequence of actions required from personnel, including established evacuation routes, designated safe rooms, and precise instructions for notifying local police dispatch. Employees must be trained on how to react under intense stress, prioritizing evacuation when a safe route exists, hiding when exit routes are compromised, and fighting back only as an absolute last resort. Furthermore, the plan should designate a specialized internal response team tasked with managing the immediate aftermath, which includes coordinating medical care and securing the facility. This response framework must undergo regular operational testing and evaluation to ensure every worker can execute their assigned duties fluidly during a chaotic emergency. Finally, the overall effectiveness of these safety mechanisms is dictated by the role of management in deliberately cultivating a supportive, completely violence-free workplace culture. Leadership must go beyond merely publishing a written policy by actively demonstrating an ongoing commitment to mental health resources, employee assistance programs, and open workplace dialogue. When supervisors actively model respectful communication and decisively address bullying or harassment, they establish an environment where workplace violence is fundamentally incompatible with daily operations. By actively integrating these comprehensive security principles into standard management practices, an organization can maintain an environment where risks are recognized early and resolved safely. See you in the next lecture. NAVEX Plus 2. Hello, and welcome back to the course. When we look at workplace safety, we often frame it in terms of compliance, rules, and regulatory oversight. However, building an effective safety and health program requires us to shift our perspective from a reactive model to a proactive design. A reactive model waits for an accident to occur, computes the damages, and then attempts to patch the flaw that caused the failure. This approach is highly inefficient and expensive, both in financial capital and human cost. Accidents incur immediate direct costs, such as workers' compensation claims, medical expenses, and legal fees, but they also carry massive indirect costs. These indirect costs include lost productivity, equipment damage, the expense of training replacement workers, and a severe degradation of workforce morale. By shifting to a structured safety culture, an organization treats safety as a core operational constraint, much like quality control or budget management. The tangible benefits of this proactive posture are clear, resulting in fewer injuries, lower insurance premiums, and a more stable, predictable production environment. EHS Insight. An effective safety program relies on specific architectural elements that must work together seamlessly to be successful. The first foundational pillar is management leadership, which requires executives and supervisors to demonstrate an active, visible commitment to safety principles. This means management must allocate actual financial resources, establish clear safety goals, and integrate safety metrics directly into regular business performance reviews. The second vital pillar is worker participation, which ensures that the people closest to the operational hazards have a meaningful voice in the system. Workers must be actively involved in setting safety goals, reporting hazards, and inspecting work areas without any fear of retaliation or negative consequences. When management leadership and worker participation are aligned, the safety program ceases to be a top-down mandate and becomes a collaborative organizational habit. This alignment establishes a psychological safety net where identifying a hazard is viewed as a valuable contribution to the company rather than a disruptive complaint. Clarion Safety Systems +2. The third core element of a resilient safety program is systematic hazard identification and assessment. This process requires regular, documented walkthroughs to evaluate risks, analyze incident trends, and catch vulnerabilities before they manifest as injuries. Once a hazard is identified, the organization applies the classic hierarchy of controls, prioritizing elimination or engineering solutions over administrative rules and personal protective equipment. The fourth essential element is comprehensive safety education and training, which provides workers with the specific technical knowledge required to perform their tasks safely. Training cannot be a one-time onboarding event. It must be an ongoing, repetitive practice that evolves alongside operational changes. Managers must also be trained to understand their unique responsibilities in protecting worker rights and addressing safety reports systematically. By institutionalizing these evaluation and training loops, an organization ensures that its safety protocols remain accurate, relevant, and highly effective over time. EHS Insight +3. To ensure continuous improvement, a modern safety program must establish objective performance metrics and regular evaluation protocols. Relying solely on lagging indicators, such as injury rates or total lost workdays, is insufficient because these numbers only tell you what went wrong in the past. An effective system balances lagging metrics with leading indicators, which track proactive safety behaviors and activities. Leading indicators include tracking the number of safety hazards reported and resolved, the completion rate of scheduled equipment maintenance, and total employee training hours. By analyzing these data points, management can identify systemic weaknesses in the safety program long before an actual incident occurs. This data-driven approach allows the company to adjust its processes, optimize resource allocation, and continually refine its operational workflows. Ultimately, integrating safety directly into daily production workflows leads to a highly efficient, fully compliant, and sustainable work environment for everyone. EHS Insight. Thank you for your time, and I will see you in the next lecture. Welcome back. When we examine occupational hazards, we often focus on heavy machinery, electrical systems, or hazardous chemicals within the factory walls. However, data from the Bureau of Labor Statistics consistently demonstrates that motor vehicle incidents are the leading cause of work-related fatalities across all industries. This reality means that for many employees, the most dangerous part of their workday is the time spent behind the wheel of a company vehicle or operating a personal car on company business. The roadway is not a controlled factory floor, which introduces an environment where predictability drops and risk increases exponentially. Understanding how to manage this risk is a core component of maintaining operational safety and preserving human life. To effectively mitigate transportation hazards, we must first categorize the specific behaviors and conditions that degrade driving safety. Voxel AI plus 3. Distracted driving represents a primary threat to driver safety, and it extends far beyond texting or handling a mobile phone. Cognitive distraction occurs anytime a driver's mental focus is diverted from the task of operating the vehicle, such as interacting with complex navigation systems or hands-free communication devices. Visual and manual distractions, like adjusting climate controls or reaching for an object, directly increase the probability of a collision because they remove the driver's eyes and hands from their primary functions. Even a momentary diversion of attention at highway speeds means a vehicle travels hundreds of feet without active human control. Employers and employees must recognize that a strict no distraction policy is not merely a legal compliance check, but a foundational safety protocol. Eliminating these internal disruptions is the first proactive step an operator can take toward ensuring a safe journey. OSHA, European Union. Driver fatigue is another critical risk factor that acts much like chemical impairment on human cognitive and physical capabilities. Prolonged periods of wakefulness degrade reaction times, diminish situational awareness, and impair the micro-decisions required to safely navigate traffic. In an industrial context, scheduling pressures or long shifts can inadvertently contribute to drowsy driving if operators do not actively manage their rest. The National Transportation Safety Board frequently identifies fatigue as a root cause in heavy vehicle accidents. To combat this, drivers must establish realistic daily mileage goals and integrate mandatory rest periods, typically stopping every 2 hours to step out of the vehicle and refresh. Recognizing the early signs of fatigue, such as frequent yawning or drifting across lane markers, must be met with an immediate decision to pull over safely rather than attempting to push through the discomfort. Study.com. Operating a vehicle changes dramatically when the payload shifts from a solo driver to one carrying passengers or heavy equipment. Transporting other personnel introduces a social dynamic that can increase driver distraction, and it places a higher ethical and operational burden on the driver to ensure compliance with all safety protocols. When a vehicle is loaded with heavy industrial equipment or tools, the physical properties of the transport alter fundamentally. The center of gravity rises, which increases the risk of a rollover during sudden evasive maneuvers or sharp turns. Furthermore, the total mass of the vehicle escalates, which significantly lengthens the stopping distance required to avoid an obstacle. Drivers must ensure that all cargo is mechanically secured using appropriate tie-downs to prevent weight shifts during transit, and they must adjust their speed downward to compensate for the modified handling characteristics. Defensive driving techniques provide the operational framework needed to survive the unpredictable behavior of other motorists and changing road conditions. At its core, defensive driving requires an operator to continuously scan the roadway ahead, creating a wide visual field to anticipate potential hazards before they materialize. Maintaining a safe following distance is a non-negotiable metric within this methodology, as it provides the necessary time buffer to react to sudden braking. Drivers must also explicitly adjust their operating habits to account for adverse environmental conditions, such as reducing speed during rain, snow, or fog, where tire traction decreases. A defensive driver assumes that other road users may commit errors or violate traffic laws, and therefore positions their vehicle to maintain an escape route at all times. This mindset shifts driving from a passive, reactive activity to an active discipline of risk management. National Association of Safety Professionals. No amount of defensive driving skill can compensate for a vehicle experiencing a catastrophic mechanical failure due to neglected maintenance. A comprehensive preventative maintenance program is a leading indicator of fleet safety and must include systematic, documented checks of critical components. Before any trip, an operator should conduct a pre-trip inspection focusing on tire pressure, tread depth, fluid levels, and the functionality of all exterior lighting and signals. Brakes, steering mechanisms, and suspension systems must be serviced on a strict schedule determined by mileage or time intervals to ensure reliability under load conditions. If an inspection reveals a defect, such as a worn brake pad or a damaged windshield wiper, the vehicle must be removed from service immediately until qualified personnel perform the repairs. Treating vehicle maintenance as an afterthought directly invites mechanical failure at the most critical operational moments. OSHA +1. Adherence to traffic laws and company safety policies forms the legal and structural baseline for minimizing roadway incidents. Speed limits are engineered based on roadway design, visibility, and traffic density. Exceeding them reduces a driver's processing time and increases impact forces geometrically during a crash. Beyond statutory laws, organizational policies must explicitly mandate the use of seatbelts for all occupants across every single trip, regardless of distance. Occupational safety data confirms that using a seatbelt cuts the risk of fatal injury by nearly half, making it the single most effective occupant protection device available. Finally, there is an absolute zero-tolerance standard for operating any vehicle while impaired by alcohol, illicit drugs, or prescription medications that cause drowsiness. Clear, enforced protocols surrounding compliance ensure that safety remains a measurable expectation rather than a subjective preference. National Association of Safety Professionals +1. See you in the next lecture. Welcome back. When we look at hot work operations like welding, cutting, and brazing, we are dealing with processes that introduce several distinct vectors of risk simultaneously. It is helpful to categorize these into chemical, physical, and electrical hazards rather than viewing them as a single, uniform danger. To understand the operational reality, we must first address the chemical and atmospheric risks, specifically the generation of toxic fumes and gases. When an electric arc or a gas flame interacts with a base metal, a flux, or a consumable electrode, it causes a rapid vaporization and subsequent condensation of fine particulate matter. This particulate matter often includes hazardous elements like hexavalent chromium from stainless steel, manganese from carbon steel, or lead from painted coatings. If you fail to account for these airborne contaminants, they can quickly accumulate in the worker's breathing zone, leading to acute respiratory irritation or severe long-term chronic illness. Mitigating these atmospheric hazards requires a systematic approach to engineering controls, primarily focused on proper mechanical ventilation. OSHA specifies exact parameters for when mechanical ventilation is mandatory, such as when a workspace is less than 10,000 cubic feet per welder, when the ceiling height is under 16 feet, or when structural barriers obstruct the natural cross-ventilation. To effectively control the exposure, local exhaust ventilation via a movable hood positioned close to the welding arc is preferred over general dilution ventilation because it captures the contaminants directly at the source. The system must pull the air away from the welder's face and exhaust it into the open air, completely away from any fresh air intakes. When engineering controls cannot reduce exposure limits below the threshold, personal protective equipment in the form of respiratory protection becomes a necessary dependency. Employers must implement a comprehensive respiratory protection program to ensure that the selected filters are appropriate for the specific metals and fluxes in use. Beyond the atmospheric threats, the physical hazards of non-ionizing radiation and extreme thermal energy demand rigorous barrier controls. The electric arc used in arc welding processes emits intense ultraviolet and infrared radiation that can cause immediate physiological damage. Direct exposure to ultraviolet rays results in photokeratitis, a painful condition commonly known as arc eye or flash burn, which is essentially a sunburn on the surface of the eye. To prevent this, operators and anyone in the immediate vicinity must use specialized personal protective equipment, specifically welding helmets equipped with the correct filter lens shade number. For instance, standard shielded metal arc welding with typical electrodes generally requires at least a shade 10 or higher filter to protect the eyes from optical radiation. Furthermore, because these rays can also cause severe burns on exposed skin, workers must wear fire-resistant clothing, heavy leather gloves, and high-top leather boots to act as physical shielding against both radiation and flying sparks. The presence of intense thermal energy also means that fire prevention must be treated as an architectural constraint of the work area before hot work begins. Sparks and slag generated during cutting or welding can fly up to 35 feet from the point of operation and can smolder undetected in cracks, floor openings, or insulation. Therefore, OSHA standards dictate that all movable combustible materials within a 35-foot radius must be completely removed from the area. If the object to be welded cannot be moved and the surrounding fire hazards cannot be relocated, you must use fire-resistant shields or guards to confine the heat and sparks. This is a strict dependency. You cannot safely proceed with hot work if flammable materials are left unprotected. Special care must also be taken when welding on metal walls or partitions, as heat can be conducted through the metal and ignite hidden combustibles on the opposite side. To manage the residual risk of ignition that remains despite clearing the area, you must establish a dedicated fire watch. A fire watch is not a passive observation role. It requires a trained individual whose sole responsibility is to monitor the hot work area for fires. This individual must have suitable fire extinguishing equipment readily available, be fully trained in its operation, and know exactly how to sound the building alarm if a fire exceeds their capacity. The fire watch must remain at the station during the entire operation and continue monitoring for at least 30 minutes after the welding or cutting is completed. This time buffer is crucial because smoldering fires often take several minutes to develop into visible flames. For operations near combustible walls or where sparks could fall through floor openings, a fire watch may also be required on the opposite side of the wall or on the floor below. Electrical safety introduces another layer of operational risk that is particularly acute in arc welding processes. The welding circuit uses an electric current to create the arc, which means the welding machine, electrode holder, and welding cables are all part of a live electrical system. If the insulation on a welding cable is cracked or frayed, or if a connection is loose, it can expose the operator to dangerous electrical shocks. This hazard is magnified if the welder is working in wet or damp conditions, or if they are sweaty, as moisture significantly reduces the electrical resistance of the human body. To maintain a safe system, all equipment must be inspected before use, and cables must be routed clear of walkways, ladders, and stairways to prevent both physical damage to the cable and tripping hazards for others. When the operation is suspended for a break or overnight, the electrodes must be removed from the holder, and the machine must be disconnected from its power source. Finally, gas welding and cutting equipment require specific handling protocols to prevent catastrophic failures related to high-pressure cylinders and flammable gases. Oxygen and fuel gas cylinders, such as acetylene, must be securely stored, handled, and chained in an upright position to prevent them from falling or being damaged. Acetylene is highly unstable at high pressures, so the system pressure must be carefully regulated according to the manufacturer's parameters. Leaking gas in a confined space can easily create an explosive atmosphere, which is why torch valves must be closed tightly when not in use. If the hot work is suspended for a substantial period, the gas supply must be positively shut off at a point outside the confined area, and the torch and hose should ideally be removed from the space entirely. By treating these requirements as strict, non-negotiable prerequisites, you can ensure compliance with OSHA standards and protect the entire workspace. See you in the next lecture. CDC +4. Hello and welcome back. When we look at complex industrial machinery, we must recognize that energy exists in many forms beyond simple electricity. Mechanical, hydraulic, pneumatic, chemical, thermal, and gravitational forces represent latent hazards that can cause severe injury or death during equipment servicing and maintenance. The core objective of an energy control program, as mandated by Standard 29 CFR 1910.147, is to prevent the unexpected startup, energization, or release of this stored energy. To achieve this, an employer must establish a comprehensive program comprising 3 structural pillars: documented machine-specific energy control procedures, rigorous employee training, and periodic annual inspections. We distinguish between 2 primary roles within this system: authorized employees, who physically implement the lockout or tagout procedures to perform maintenance, and affected employees, whose daily job responsibilities require them to operate or work around the machinery undergoing service. The execution of hazardous energy control follows a strict, sequential protocol that leaves no room for deviation or improvisation. The process begins with preparation, where the authorized employee must thoroughly identify all energy types, their magnitudes, and the specific hazards associated with the machine's power sources. Once identified, the next step requires explicit notification to all affected employees that the machine is being shut down and isolated. Only after this notification can the actual machine shutdown occur, utilizing normal operating stop controls rather than emergency stops, which could introduce erratic system behaviors. Following shutdown, machine isolation must be achieved by physically operating the energy isolating devices, such as manually operated electrical circuit breakers, disconnect switches, line valves, or blocks, separating the equipment entirely from its energy infrastructure. With the equipment completely isolated, the authorized worker applies the physical lockout or tagout devices to each energy isolating component. Lockout devices utilize a positive mechanical means, such as a dedicated padlock or a multi-lock hasp, to hold an isolating switch or valve in a safe, non-functional position. Tagout devices are prominent warning mechanisms, including standardized tags and durable fasteners with a minimum unlocking strength of 50 pounds, which specify that the equipment must not be operated. OSHA strictly dictates that lockout is the preferred method. Tagout may only be utilized if an energy isolating device is mechanically incapable of being locked out, or if the employer can demonstrate that a tagout system provides a level of safety equivalent to an actual physical lock. These protective devices must be standardized by color, shape, or size within the facility, must uniquely identify the authorized employee who applied them, and must never be used for any other purpose. Once the physical locking hardware is securely attached, the procedure moves into the critical phase of managing residual or stored energy. Latent energy can linger within a system long after the main power supply has been completely disconnected. Authorized workers must systematically relieve, disconnect, or restrain this residual energy by discharging electrical capacitors, releasing compressed air or fluid pressure from hydraulic and pneumatic lines, bleeding lines, and physically bracing or pinning elevated mechanical components that could fall under gravitational forces. If there is any credible potential for the reaccumulation of stored energy to hazardous levels, the worker must maintain continuous or periodic monitoring throughout the maintenance operation to ensure the system remains entirely inert. The absolute final step before any physical tool touches a machine component is the verification of complete isolation. The authorized employee must actively test the equipment using the standard local start controls to confirm that the machine cannot be energized. This is a critical physical validation step often described in industrial settings as trying out the system to ensure zero energy state achieved. During this verification process, all nearby personnel must stand completely clear of any potential danger zones in the event that an isolation point fails. Once the local control test proves negative, the authorized worker must immediately return the operating controls back to the neutral or off position to prevent an automatic restart when power is eventually restored. When maintenance work is finalized, a structured, reverse sequence must be followed to safely remove the locks and tags and restore power. The authorized employee must inspect the entire work area to ensure that all loose tools have been removed, that all protective mechanical guards are completely reinstalled, and that the machine is physically intact. Next, the worker must ensure that all employees are safely positioned away from the machinery and actively notify all affected personnel that the lockout devices are about to be removed. As a strict regulatory rule, each lockout or tagout device must be removed exclusively by the specific authorized employee who originally applied it to the energy isolating mechanism. In rare emergency situations where that individual is entirely absent from the facility, the employer may follow a highly regulated, documented exception procedure to remove the lock, which requires verifying the employee's absence and ensuring they are informed of the removal immediately upon returning to work. See you in the next lecture. EHA's Careers +3. Welcome back. When we manage workplace hazards, it is easy to focus exclusively on obvious chemical targets like bulk solvents or liquid acids. But a comprehensive safety strategy requires an awareness of less visible materials that pose severe physical risks. Materials like combustible dust, highly pressurized compressed gases, and chemically reactive substances can create devastating events if they are mishandled or stored incorrectly. Our architectural goal in any industrial facility is to design out these risks by applying solid engineering controls and understanding how materials behave in a given space. It is a fundamental truth that you cannot control a risk you do not recognize, which is why we must treat these advanced hazardous materials with the same structural discipline we apply to standard industrial liquids. Over the next few minutes, we will break down exactly how these materials behave and how you can establish effective containment and ventilation to prevent catastrophic system failures. Let us begin with combustible dust, which represents a massive risk in manufacturing environments but is frequently overlooked because the individual particles seem completely harmless. When fine solid materials accumulate on rafters, light fixtures, or inside ductwork, they create a hidden reservoir of fuel just waiting for an ignition source. OSHA defines combustible dust as any fine material that can catch fire and explode when mixed with air in the proper concentration. The danger escalates dramatically due to a phenomenon known as a secondary explosion, where a small initial blast disturbs accumulated dust on overhead surfaces, creating a massive airborne cloud that ignites into a second, much larger explosion. To prevent this, facilities must implement strict housekeeping to prevent dust accumulation beyond a layer thinner than a standard paperclip. Furthermore, localized exhaust systems must pull dust away from the point of generation, ensuring that concentrations never reach the lower explosive limit within the shared airspace of the facility. Compressed gases introduce a completely different set of structural challenges because they combine chemical hazards with extreme mechanical energy. A standard pressurized gas cylinder acts as a potential rocket if its valve is sheared off, which is why OSHA Standard 1910.101 emphasizes rigid physical security for every single container. Cylinders must always be stored in an upright position and secured with chains, straps, or dedicated racks to completely eliminate the risk of tipping. They must also be kept away from direct heat sources, open flames, and areas where temperatures could exceed 125 degrees Fahrenheit, as internal pressure increases proportionally with temperature. We must also pay special attention to the mechanical integrity of the valves, ensuring that heavy protective caps remain securely screwed in place whenever a cylinder is not actively hooked up to a distribution system. If a cylinder contains a flammable gas like acetylene, It is also critical to understand that it must never be stored horizontally, as this can cause the stabilizing solvent inside to leak out and destabilize the gas. Reactive substances require a deep understanding of chemical compatibility because these materials can undergo violent transformations when exposed to air, water, or other chemicals. Pyrophoric materials will ignite spontaneously in air, while water-reactive compounds will produce flammable or highly toxic gases the moment they contact moisture. This means that storage is not just about keeping a roof over the container. It is about controlling the exact environmental conditions inside the storage room. We must segregate incompatible materials completely, keeping oxidizers at least 20 feet away from flammable gases or separating them with a non-combustible firewall that has a fire resistance rating of at least 1/2 hour. When dealing with highly reactive substances, you should never rely on a single barrier, which brings us to the crucial safety concept of secondary containment. Secondary containment systems act as a critical second line of defense designed to capture hazardous materials if the primary container suffers a structural failure. If a drum leaks or a pipe ruptures, secondary containment ensures the spill is restricted to a controlled zone rather than reaching for drains, walkways, or adjacent storage areas. To comply with standard safety practices, a containment system like a spill pallet or a curb concrete dike must possess enough volume to hold 100% of the largest single container or 10% of the total volume of all containers stored within it, whichever number is greater. The containment materials themselves must be chemically compatible with the stored substance. For example, you would never use an unlined concrete floor to contain strong acids that can eat through the matrix. By keeping spills localized, we prevent incompatible chemical reactions and buy valuable time for emergency response teams to neutralize the material safely. To keep these environments stable, mechanical ventilation is an absolute prerequisite for any area handling volatile or reactive hazardous substances. Dilution ventilation replaces contaminated air with fresh air to keep hazardous vapors below permissible exposure limits, while local exhaust ventilation captures contaminants directly at their source before they can disperse. This is especially vital when dealing with toxic compressed gases or materials that slowly off-gas over time. Along with proper airflow, the physical workplace must feature readily accessible emergency response equipment, including safety showers, eye-wash stations, and appropriate fire suppression systems. This equipment must remain completely unobstructed and positioned within a 10-second walking distance from the hazard zone, ensuring that if a chemical reaction or exposure occurs, mitigation can begin immediately. Managing these hazardous materials requires continuous vigilance, proper engineering controls, and a strict adherence to storage thresholds to maintain a safe operational environment. See you in the next lecture. Hello, and welcome back. When we consider the architecture of a robust safety management system, we must look beyond physical guards and written compliance documents to the underlying human dynamics. A truly effective organization operates not merely on external regulations, but on an internal, shared commitment to zero-incident outcomes. This state cannot be achieved through passive adherence to rules, nor can it be sustained by management decree alone. It requires an intentional shift away from a compliance-focused mindset, where individuals do the bare minimum to avoid penalties, toward a values-driven mission where every participant takes personal ownership of the operational environment. To lead this transformation, you do not need an official title, because true leadership in this context is defined by individual initiative and the continuous, small actions that collectively reshape how a team perceives risk and responsibility. Uni Athena. At the core of a zero-incident culture is the deliberate communication of safety as a foundational value rather than an administrative priority. Priorities change based on production demands, schedule pressures, and economic factors, but values remain constant regardless of external conditions. When you communicate about safety with your peers, The language should shift away from bureaucratic checkboxes and focus on the real, human impact of our operational choices. For example, explaining how a correct material handling technique prevents a chronic, debilitating back injury is far more effective than simply stating that a policy must be followed. By consistently framing procedures around the preservation of health and well-being, you help your team internalize the rationale behind the rules, making safe behavior a natural default rather than an enforced chore. Athena. Influencing peer behavior on the shop floor or in an industrial facility relies heavily on the psychological principle of positive reinforcement rather than punitive measures. Historically, organizations attempted to discipline their way to safety, a strategy that invariably fails because it drives problem reporting underground and breeds resentment. If you observe a coworker taking the extra time to properly secure an electrical lockout device or clear a transient tripping hazard from a walkway, acknowledging that specific action creates a powerful feedback loop. This positive recognition validates the individual's choice and establishes a visible benchmark for the rest of the team. Over time, these reinforced actions develop into shared behavioral norms, where peer influence naturally corrects at-risk behaviors before they escalate into measurable workplace incidents or injuries. Associates. A critical component of this cultural evolution is the active mentorship of newer or less experienced employees who enter the workplace. New workers are statistically more vulnerable to incidents due to unfamiliarity with specific operational hazards and a frequent desire to prove their efficiency by working quickly. By taking the initiative to guide these colleagues, you demonstrate that safety and operational velocity are not mutually exclusive goals. Mentorship does not mean lecturing, but rather demonstrating correct techniques in real time and openly explaining the situational hazards associated with the task. When experienced workers model meticulous safety habits, they pass on critical institutional knowledge and signal to new hires that the organization values precision, patience, and mutual protection over reckless shortcuts. True transparency requires a psychological environment where reporting hazards, errors, and near misses is actively encouraged and completely protected from negative repercussions. If a team member fears reprisal, blame, or administrative penalties for identifying a system flaw, they will hide the issue, leaving the underlying hazard active and waiting to cause a future incident. Building psychological safety means treating every reported near miss as a free learning opportunity for the entire organization rather than a personal failure of the operator. When an individual flags a leaking hydraulic line or an unguarded piece of machinery, the contribution must be welcomed with gratitude and addressed transparently. When the workforce sees that their reports directly lead to tangible engineering improvements, trust is solidified, and the reporting mechanism becomes a proactive tool for continuous risk reduction. Associates +1. While peer interaction forms the foundation, sustaining this culture requires effectively voicing safety concerns to upper management when structural or financial changes are necessary. Approaching management with a safety issue should be handled with the same professionalism as presenting a production optimization plan. Instead of simply presenting a vague complaint about a tool, clearly define the specific hazard, reference the potential operational impact, and propose a viable, collaborative solution. For instance, if a ventilation system in a chemical storage area is degrading, present data on exposure risks alongside a plan for stage maintenance that minimizes production downtime. This constructive approach positions safety as a core component of operational excellence, making it easier for management to allocate resources and collaborate on systemic improvements. Ultimately, achieving a zero-incident workplace is an ongoing collaborative process that recognizes safety as a deeply shared responsibility. It functions much like a well-designed software ecosystem, where every component must reliably fulfill its contract for the entire system to remain stable. No single safety officer or supervisor can observe every action or identify every latent hazard in a dynamic industrial environment. It is the collective vigilance of the individuals performing the work that determines the ultimate success of the program. By remaining actively engaged, supporting your peers, and insisting on absolute transparency, you play a direct role in transforming your workplace into a proactive community where everyone returns home safely at the end of every shift. See you in the next lecture. Welcome back to this final session of our comprehensive safety journey. We have covered an extensive amount of ground across the regulatory and operational spectrum of general industry safety, and now it is time to formalize the completion of your training. Completing these 10 hours of instruction represents a significant milestone, but the true value of this effort lies in how you apply these principles moving forward. Safety is not a static milestone or a bureaucratic checkbox. It is a continuous operational process that requires daily vigilance and an active commitment from every individual on the shop floor. Your primary responsibility from this point onward is to remain highly observant, identify potential hazards before they escalate, and immediately report unsafe conditions through your organization's established channels. An effective safety program relies entirely on the willingness of workers to speak up and actively contribute to maintaining a secure environment. By applying the hazard communication, electrical safety, and material handling principles we discussed, you become the most effective tool your company has for preventing workplace injuries and ensuring that every employee returns home safely at the end of every shift. Now that you have fulfilled the rigorous instructional hour requirements, the administrative process for receiving your official Department of Labor card begins. Your training provider will submit the documentation of your successful completion directly to the Occupational Safety and Health Administration for processing. Because OSHA strictly audits these records to maintain the integrity of the program, the issuance and delivery of your physical card can take anywhere from 4 to 8 weeks. While you wait for the official card to arrive in the mail, you should receive a temporary digital certificate of completion. It is critical to keep this digital documentation safe, as many employers and job sites require immediate verification of training before you can legally access certain operational areas or begin work. Beyond the initial receipt of your card, you must take proactive steps to maintain your continuing education and training records systematically. OSHA general industry cards do not technically expire at the federal level, but many state jurisdictions, municipal building codes, and private employers enforce a mandatory renewal policy every 3 to 5 years to account for regulatory updates. You should treat this certification as a foundational component of your professional records, documenting the exact completion date and storing digital backups securely. When your organization conducts periodic safety refreshers or specialized training sessions, ensure that your participation is documented and added to your personal compliance file. Maintaining a clear, chronological history of your safety training demonstrates regulatory compliance during internal audits or official agency inspections. Remaining compliant also requires a reliable mechanism for staying updated on changing standards, as regulations are continuously updated to address emerging industrial risks. The official federal website serves as the primary source for all regulatory updates, where the agency publishes notices of proposed rulemaking, final rules, and official letters of interpretation that clarify complex standards. You can subscribe to the agency's electronic newsletters and enforcement updates to receive direct notifications when specific standards under general industry regulations are amended. Additionally, reviewing the regional enforcement emphasis programs published on the agency's portal gives you direct insight into the specific hazards compliance officers are actively targeting during unannounced workplace inspections. Keeping pace with these administrative adjustments ensures that your facility's safety programs remain accurate and fully aligned with current federal expectations. Thank you for your dedication to workplace safety throughout this comprehensive course. Goodbye for now, and stay safe out there.